Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 17. Today we're going to talk about autonomous nonlinear systems. As you recall, these systems have this form, where in particular the function on the right-hand side does not depend upon the independent variable t. In this case, there are values of x naught which equal 0 when substituted into the right-hand side. These are places where the derivative is 0, and hence these are equilibria. We are going to get some idea of the nature of solutions in a neighborhood of equilibria by analyzing the linearization. If you'll think back to Taylor's theorem, or Taylor's series from Calculus 2, you had a function is equal to f of x naught plus f prime of x naught times x minus x naught plus 1 over 2 factorial f double prime at x naught times x minus x naught squared, and so on forever. We get equality only when the function itself is analytic. In the present case, we're not dealing with scalar valued functions, so the meaning of the derivative here needs to be explored. In the multivariable case, at least we can say the following. The vector valued function of a vector variable will be the function evaluated at some point plus df at x naught times, and we'll have to talk about what we mean by times, x minus x naught plus higher order terms. We'll not worry about these higher order terms. We're going to perform the linearization. We'll suppose that we're dealing with an equilibrium point, and hence this will be the zero vector. That makes our solutions near equilibria dependent upon the nature of this object, whatever it is. If f has the form f1 of x, f2 of x, fn of x, then df of x will consist of partial derivatives of each of these functions in the following way. df1 dx1, df1 dx2, dfn dxn. We'll assume that we have n entries here and each x has n coordinates as well. Down to dfn dx1. Notice that each row is the gradient of the coordinate function. You can see then we will have an n by n matrix. And the type of multiplication that we have in multiplying this matrix by x minus x naught is regular matrix multiplication. This will be an n by n matrix. This will be n by 1, where we're assuming the vector x has coordinates x1, x2 through xn. Now if x naught is an equilibrium point, then the differential equation takes the following form. Keep in mind f of x naught is the zero vector. You'll have df at x naught as a matrix times, it's a matrix evaluated at a particular point, making it a constant matrix, times x minus x naught plus higher order terms. We're going to assume that the distance between x and x naught is so small that the higher order terms involving squares of those coordinates will be so small as to be negligible. Our original derivative then will only be approximately equal to df of x naught times x minus x naught. We're almost at the point where we can describe the entire linearization. First, I need to point out that the derivative of x with respect to t gives you the same result as the derivative of x minus x naught with respect to t, since x naught is a constant point. What we'll do is we'll set w to be x minus x naught. The linearized system is then dw dt equals df at x naught times w. This then is a homogeneous constant coefficient linear system. We know how to solve all of these, and we can classify the solutions using our eigenvalues of the coefficient matrix, the matrix of partial derivatives of our coordinate functions. Before proceeding to examples, we need to give a few definitions concerning stability. These concern the IVP dx dt equals f of x, x of t naught equals x naught. Let x naught be an equilibrium point of the IVP star. We'll call this star. We say that x naught is stable if for each neighborhood u of x naught. By the way, a neighborhood is any open set that contains this point. There exists another neighborhood u bar, which is a subset of u, such that if x1 is an element of u bar, then the solution to x dot equals f of x, x of t naught equals x1, if we start instead of at x naught at the point x1 in some close neighborhood of x naught, satisfies the solution x stays within u for all t greater than t naught. This says that as long as you stay within some neighborhood of x naught, let's suppose that here's our coordinate system, this is the point x naught, choose some open neighborhood u, there's going to be some smaller neighborhood u bar, so that if you choose an initial point x1 within this neighborhood, the solution starting there won't stray too far, won't stray outside of the neighborhood u from the point x naught. From our experience with linear systems, we see that centers are stable, but so are sinks and spiral sinks. So sinks, spiral sinks, and centers are all stable. Obviously, an equilibrium point is unstable if it is not stable. From what we've discussed so far, we know that sources spiral sources and saddle points are all unstable. There's a little bit more nomenclature we need to add. If for x1 in some neighborhood u, of x naught, we have for solutions to the initial value problem, x dot equals f of x, x of t naught equals x1, the following condition, the limit as t goes to infinity of x of t equals x naught. We say that x naught is asymptotically stable. In this case, if you perturb off of the equilibrium point x naught just a little bit, x1, within some neighborhood, the solution will tend back towards the initial point x naught, the equilibrium point x naught, as t goes to infinity. That's what we mean by asymptotically stable. Sinks are always asymptotically stable. Note that while sinks are asymptotically stable, centers are stable but not asymptotically stable. For a center, you don't trend back towards the equilibrium point. You always stay some fixed distance away from it, following in some closed cycle. Adding to this last definition, if in the limit as t goes to minus infinity, x of t, you get x naught, we call the equilibrium point at x naught asymptotically unstable. In this case, as you go backwards in time, here's forwards in time, if you go backwards in time as t goes to minus infinity, you end up back at the equilibrium point. So this is an example of something that is asymptotically unstable. You can see that spiral sources as well as sources are asymptotically unstable. We're ready now to look at an example. Let's suppose that we have dx dt is x times 1 minus x minus y. dy dt is y times 1 minus 2x minus 3y. So that our vector x has variables x and y. We find equilibria by setting the right-hand sides equal to 0. I want you to think a little carefully about the logical structure of these equations. When I have two things multiplied together equaling 0, we may use the zero product theorem to solve this kind of equation. The zero product theorem says that if I have a times b equaling 0, then either a is 0 or b is 0 or both. So we deduce that x is 0, or if this is 0, then x plus y equals 1. But at the same time, to be in equilibrium, both this equation must be 0 and this equation must be 0. So in between that or statement, we have an and statement. Y is 0 or 2x plus 3y equals 1. This allows us to make one of four combinations. This allows us to make four different possible combinations. We either have x equals 0 and x equals 0, giving us an equilibrium point at the origin. If x is 0 and this other equation holds, with x equals 0, we deduce that y is 1/3. Alternatively, if y is 0 and this other equation holds, then x is 1. And there's one more possible combination. We can have these two equations hold. In that case, we're going to have to solve that linear system. If x plus y is 1 and 2x plus 3y is also 1, we can solve this linear system of equations any number of different ways. Let's use Cramer's rule. The denominator for x is going to be the coefficient matrix 1, 1, 2, 3. The numerator is obtained by replacing the x coefficients with the right-hand sides. So we end up with 1, 1 down the first column and 1, 3 down the second column. The numerator is going to be 3 minus 1, which is 2, and the denominator is going to be 3 minus 2, which is 1. That gives us an x value of 2. Note that if x is 2, then y must be negative 1, giving us the final equilibrium point. You're going to need to remember how we solved that system of equations for the exam. Keep in mind our equations are x dot equals x times 1 minus x minus y. Y dot is y times 1 minus 2x minus 3y. We're now going to distribute these leading factors here. We'll have x minus x squared minus xy and y minus 2xy minus 3y squared. We're now going to calculate the derivative of the function on the right-hand side. The matrix of derivatives is 1 minus 2x minus y. Make sure you know how to calculate these derivatives. The derivative of x is 1, the derivative of x squared is 2x, and on the next term we're holding y constant, and so it comes along as a factor. Derivative of x is 1, and that's why we get minus 1 times y. We now have to take the derivative with respect to y, holding x constant. If x is held constant, its derivative is 0. 0. Taking the derivative of the last term with respect to y, we get minus x. Let's do that on the next term. Taking the derivative with respect to x, holding y constant, the first and the last terms will have derivatives equal to 0. The middle term will have derivative negative 2y. Now we take the derivative with respect to y. That gives 1 minus 2x minus 6y. We can now classify these equilibrium points by looking at the eigenvalues of the matrix of partial derivatives evaluated at the equilibria. So first, let's evaluate the matrix of partial derivatives at the equilibrium point 0, 0. We'll have 1, 0, 0, 1. Notice that the eigenvalues are both 1, multiplicity 2, algebraic multiplicity 2, geometric multiplicity also 2. This will be an asymptotically unstable source. Evaluating at 0, 1/3, if x is 0 and y is 1/3, we'll have 2/3 here, 0, negative 2/3, x is 0, y is 1/3, negative 6 times a third is negative 2, and 1 gives you negative 1. This matrix is lower triangular, and so the eigenvalues may be read off of the diagonal. Since 1 is positive and 1 is negative, we deduce that this is an unstable saddle. At the equilibrium point 1, 0, x is 1, y is 0. We'll have negative 1, 0, y is 0, x is 1. We'll have negative 1. You can see now the eigenvalues are negative 1 and negative 1, making this an asymptotically stable sink. Finally, at 2, negative 1, x is 2, so 1 minus 4 is negative 3, plus 1 is negative 2, negative 2, positive 2, because y is negative 1, x is 2, 1 minus 2 is negative 3, negative 3 plus 6 is positive 3. Because this is neither upper triangular, lower triangular, or diagonal, we have to work a little harder to figure out the eigenvalues in this case. Towards that end, we'll subtract lambda from the diagonal elements, take the determinant, we'll have negative 2 minus lambda, 3 minus lambda, and then minus a negative 4. We'll have a positive lambda squared. Negative 2 times negative lambda is positive 2 lambda. Minus 3 lambda is minus lambda. Minus 6 plus 4 is minus 2. This factors is lambda minus 2, lambda plus 1. This gives lambda equals 2 and negative 1. That makes this an unstable saddle point. Plotting these points, we have the origin, we have 0, 1/3, we have 1, 0, and 2, negative 1. these 4 equilibrium points. The origin was a source, so points that start out in the neighborhood of the origin will tend to drift away from that point, kind of in an asymptotical way. 0, 1/3 was a saddle point, which means you go in some directions and out in others. The point 1, 0 was a sink, and so points that come out from here might tend over there. This last point was also a saddle, meaning you may go out in some directions, but in others. I'd like to consider a special form of the Volterra-Lotka predator-prey equations. There are several different forms that this can take. We're going to assume a particularly simple one. Let's suppose that we have rabbits, and the rabbits will grow exponentially if left on their own. But if there gets to be too many foxes, if the number of foxes rise above 1, then this will become negative, and that will drive the rabbit population down. We'll assume that the foxes on their own will also grow exponentially, but if there are too few rabbits, the fox population will decline. I know in practice, these numbers won't be 1 and 1, and we'll have some other coefficients here and here. Nonetheless, let's just assume all of the constants in the problem are equal to 1 to make this simple. To find the equilibria, we have to set x equal to 0 or y equal to 1, and y is 0 or x is 1. There are only 2 in this case because you can't have both x equals 0 and x equals 1, or y equals 1 and y equals 0. So you either have the point 0, 0, or you have the point 1, 1. These are the equilibria. If we multiply through, we may then find the matrix of partial derivatives. The derivative here with respect to x is 1 minus y. The derivative with respect to y is minus x. The derivative with respect to x is y. And the derivative with respect to y is x minus 1. Evaluating the matrix of partial derivatives at the equilibrium point 0, 0, we have 1, 0, 0, minus 1. The eigenvalues are 1 and negative 1, meaning that this is an unstable saddle. You might think that extinction is pretty stable, but if you perturb off of extinction, you tend to go away from it. Considering the other equilibrium point 1, 1, we're going to have 0, negative 1, 1, and 0. Since this is not diagonal, upper triangular, or lower triangular, we have to work a little harder to figure out the eigenvalues. So we subtract lambda from the diagonal elements, and we'll get positive lambda squared, and then subtract a negative 1, that's plus 1. The eigenvalues are plus or minus I. Notice that alpha is 0 in this case, and beta is 1. With alpha equal to 0, we have a stable center. With this model for rabbits and foxes, we'll constrain ourselves to an analysis of the first quadrant. We have 2 equilibrium points, 0, 0, and 1, 1. We already know that 0, 0 is unstable and is a saddle point. If you start a little bit off of here, you'll tend to drift away in one direction and towards it in another direction. In particular, the fox population, if you have only foxes, will tend to decline exponentially to 0. If you have only rabbits, the rabbit population will tend to grow exponentially. And if you have a combination of both, you'll tend to do something like this. If you perturb off of this other equilibrium point, we said that this is a center. You end up revolving around this in these closed cycles. These other cycles on a larger scale will do the following. If these are our rabbits and these are the foxes, here's how we can interpret this. At least in a neighborhood, this is like a saddle. In a larger scale, these all behave like closed cycles. You can see what happens. If you have a small number of both rabbits and foxes, the rabbits will have a chance to grow. And so they will. Up to a point. Once you get a sufficient critical mass of rabbits, the fox population will also grow. And as the fox population grows, the rabbit population declines. Foxes grow, the rabbits decline, up to a certain point. At that point, there are too few rabbits to sustain the fox population that you have, and so the fox population will decline. And you'll go around this time and again. This is called a vicious cycle. I'd like to look at this last example from a numerical perspective. Recall that we had an approximate scheme called Euler's method, and we applied it to differential equations of the form dy dx equals f of x comma y, where y of x naught was equal to some y naught. The method went like this. Xn was going to be x naught plus h times n. H is just kind of an increment in the x values. You choose h to be small to get more accurate estimations. And the new value of y was determined from the old value plus h times the function f evaluated at the old points. We can apply Euler's method to systems. To get that in the new t, you start with the initial t and add n increments of h. To get to the new x's, you take the old x and add h times this function evaluated at the old point. And this gives you Euler's method as applied to systems. Let's apply this to the predator-prey equations that we just analyzed. Here's how we're going to label things. We're going to have t's, x's for the rabbits and y's for the foxes, and h is our increment. T is going to start at 0. We'll start both rabbits and foxes at some small value, and we'll make our increment, say, 0.01. To get to the new t, you take the old t and add your increment, but we need to make that increment an absolute reference. To get to the new x's, we'll take the old x's and we'll add h, again, as an absolute reference, times our differential equation said the old x times 1 minus the old y. To get to the new y's, we'll take the old y plus h, again as an absolute reference, times the old y times the old x minus 1. Now we would like to do this computation maybe 100 times, so I'm going to click Control G, and I want to go to A102. That brings the entry point here. Control G is the go-to command. We're going to go back up and position the cursor right here. I'm going to press the Shift button and then click. To paste the formulas that we've entered down, I click Control G, Control D. D is in dinosaur. We now have a numerical simulation or computation estimating the solutions to this differential equation. To get a picture of how these look, I'm going to insert a chart, let's say of this form. Notice we're only getting the initial part of that cycle that shows that the origin 0 is behaving, starting at point 1, it's behaving like a saddle point. We need to do the computation a little bit further down, so I'm going to delete this graph. And instead of, I'm going to click Control Z to undo the computations that we just did. I don't want to go to only 100 iterations of the method. We're going to need to do maybe 2,000 iterations. So I'm going to click Control G, A, 2002. That brings us down to this point right here. I'm going to go over to the scroll bar and drag the scroll bar up back to the top here. If I can get it to scroll all the way back up, I'm going to press Shift, click, and then Control D. Now let's check out. I'm going to press the Shift button and click here so I get both columns. We'll insert a chart like this, and you can see the vicious cycle now going around. Notice that it forms loops that aren't quite closed. Why are these loops not quite closed? They're not quite closed because this is only a numerical simulation. If we choose h to be smaller, like 0.005, just a wee bit smaller, they should close up at that point. And, well, again, to within the numerical precision that we're plotting on this particular graph. So the smaller you make h, the better off your approximations will be, the more these loops will close up. And you can actually see the vicious cycle about the point 1, 1. If we change the initial data a little bit, close to the point 1, 1, let's say x equals 1, y equals 0.9, that puts us pretty close to the point 1, 1. And you can see the cycle going around here. 1, 1 is definitely classified as a center with eigenvalues I and negative I. You can see that right here.